Right, so Pearson's R is a measure of correlation between two quantitative variables. So for a sample statistic, we use the symbol R, and then for our population parameter, we're going to use the symbol rho. There are 5 properties of Pearson's R, so the correlation that you get will be between -1 and +1. So for a positive association, your R will be greater than 0, and for a negative association, your R will be less than 0. If there is no relationship, your R will be equal to 0. So the way that the direction of the correlation works is that the closer R is to 0, the weaker your relationship is, and the closer R is to +1 or -1, the stronger the relationship is. So the sign of the correlation is important to know that it provides direction only. Correlation is also unit-free, and the correlation between y and x is equal to the correlation between x and y. So here's just a chart to show how you can evaluate correlation coefficients. So it just shows how we can define the strength of relationship corresponding to the absolute value of R. So whether very weak, weak, moderate, strong, or very strong. It's also important to know that these categories are the exact same for the numbers if you put negative signs on both. So it's just good to know that the strength of the relationship doesn't have an effect on whether it's positive or negative. So for hypothesis testing, we have the same 5-step hypothesis testing procedure that we've done the entire semester. So for correlation, we have a couple of different assumptions, but they're still generally the same. So you first check your assumptions and write your hypotheses. Our assumptions here is that both of our variables must be quantitative, and the relationship between x and y must be linear. Also, for our hypotheses, your null hypothesis is that your rho will be equal to 0. That just means that there is no relationship between the two variables that you're testing. After you write your hypotheses, you're going to calculate your test statistic, then use that test statistic to determine the p-value. Then you make a decision whether to reject or fail to reject the null hypothesis based on your alpha level, and then state a real-world conclusion. So simple linear regression is when you use one or more explanatory variables, also known as x or independent variable, to predict one response variable, which is known as y, or the dependent variable. So our formula for that is your predicted value of y for a given value of x is equal to your y-intercept plus your slope multiplied by your explanatory variable, or your x variable. So the slope is just a measure of how steep your line is, also known as rise over run if you remember from algebra. So a positive slope is when your graph is moving in the direction from bottom left to top right, and your negative slope is if you have a line in a graph moving from the top left to the bottom right. And then finally your y-intercept, which is known in the simple linear regression equation as b sub 0. That is just the predicted value of y when x equals 0. So there's 4 assumptions of the simple linear regression model. So the first is linearity, so making sure you have a linear relationship between x and y. Second is independence of error, so making sure that there is no relationship between the residuals, make sure they're independent of one another, and the y variable. Between residuals and the y variable, they are independent of one another. Third is normality of errors, so the residuals must be approximately normally distributed. If you remember that normal distribution, the bell-shaped curve. And then finally, equal variances, so the variance of residuals must be the same for all your values of x. So the confidence interval for a slope, we can just calculate that by taking our sample slope. That kind of takes the place of our sample statistic that you usually have there. So the sample slope plus or minus t star, which is the value from the t distribution. For this t distribution that we're using here, we have a degrees of freedom equal to -2. And then you multiply that by your standard error. And the standard error is just the standard error of your sample slope. So coefficient of determination is just r squared. So it's the amount of variation in the response variable that can be explained by the explanatory variable. So this is denoted by r squared. So we can calculate this coefficient of determination by just taking our Pearson's R, which is our sample correlation, and squaring it. So it's important to know the influence of outliers on a correlation. So most of the time we've seen an outlier decreasing the value of a correlation coefficient, which ultimately weakens the regression relationship. So we think of an outlier kind of ruining our relationship between our variables, but sometimes we can see that an outlier increases the correlation value and actually improves regression. So we call this an influential outlier. So you see figure 1 and 2 have the same data, except figure 1 has an outlier and figure 2 has no outlier. In figure 1, you can see the outlier circled on the top right corner. And you see how that makes more of a positive slope in our graph. When if you take that out in the second figure, you see how we have a flat line. There's really no relationship we can identify between the two variables, and you can just see how the outlier kind of manipulates that data into you thinking that there is a significant relationship between the variables. So extrapolation is when you use a regression equation to estimate the response of a data point when the value for its explanatory variable falls outside the range of the explanatory variables used to create the regression. So that's kind of a mouthful there, but it's really saying when you're using data from a certain category to try to solve for another value that is not within that same category. So for example, if you have a data set that shows the heights of adults, you could not use that data set to try to estimate the height of a child because it's just outside of the range of the explanatory variables that we use to create that initial regression, which is the height of adults. Okay, so on to the first review question. The plot shows the line, the estimated value of y is equal to 6.5 plus 1.8 times x. When x equals 0, what is the predicted value of y? All right, yeah, so our answer here is C, good job. So really just there's two ways to find this. If you can identify in the equation that you know where the y-intercept is in the equation, which is 6.5, then you would automatically know the answer. But if you weren't really familiar with that, you could just plug in 0 for the x value, and then that would ultimately give you your answer of 6.5. So good job. Second review, the correlation between quiz averages and final exam scores was R equals 0.60863. Calculate the coefficient of determination. All right, the answer here is C, 0.3704. So really, how you get your answer here to calculate R squared is taking the statistic that we're given for R and squaring that value. So 0.60863, and if you square that, multiply it by itself, you get 0.3704. All right, finally, calculate the confidence interval for a slope using the values given. So we're given a slope of 0.8034, a t-star of 2.064, and a standard error of 0.136. All right, so using the formula on the top right, you can plug in B1 as your slope, T star as 2.064, and then your standard error of the slope. So when we do that, we plug in those numbers, we get a margin of error. We can get our margin of error by multiplying 2.064 by 0.136, and we get 0.2807 as our margin of error. Then we can just add and subtract that margin of error to the slope. And then we get a confidence interval of 0.523 to 1.084. So we can say that we are 95% confident that our slope is between 0.523 and 1.084.